Hello everyone. Welcome to my channel. This is my very first video, so I hope you like it. And please subscribe to my channel. This video will be mainly about Schottky Diode. This video will cover 1. Introduction of Schottky Diode. 2. Symbol of Schottky Diode. 3. Construction. 4. Working. 5. VI characteristics. 6. Application. 7. And difference between Schottky and PN junction diode. Schottky Diode. What is a Schottky Diode? A Schottky Diode is a type of electronic component that is used in a variety of applications. It is a semiconductor device that is used as a rectifier, which means it is used to convert alternating current AC to direct current DC. Given below is a diagram of a Schottky Diode. Symbol of Schottky Diode. In Schottky Diode, the metal acts as anode and N-type semiconductor as the cathode. Now let's look at how Schottky Diode are constructed. It is a unilateral junction. A metal semiconductor junction is formed at one end and another metal semiconductor contact is formed at the other end. It is an ideal ohmic bidirectional contact with no potential existing between the metal and the semiconductor, and it is non-rectifying the built-in potential across the open-circuited Schottky barrier diode characterizes the Schottky diode. Schottky diode is a function of temperature dropping. It decreases and increasing temperature doping concentration in N-type semiconductor. For manufacturing purposes, the metals of the Schottky barrier diode like molybdenum, platinum, chromium, tungsten, aluminum, gold, etc. are used, and the semiconductor used is N-type. Now let's look at how Schottky diode works. When the metal is joined with the N-type semiconductor, the conduction band electrons, free electrons, in the N-type semiconductor will move from N-type semiconductor to metal to establish an equilibrium state. When a neutral atom loses an electron, it becomes a positive ion. Similarly, when a neutral atom gains an extra electron, it becomes a negative ion. The conduction band electrons, or free electrons, that are crossing the junction will provide extra electrons to the atoms in the metal. As a result, the atoms at the metal junction gains extra electrons and the atoms at the inside junction lose electrons. The atoms that lose electrons at the inside junction will become positive ions, whereas the atoms that gain extra electrons at the metal junction will become negative ions. Thus, positive ions are created at the inside junction, and negative ions are created at the metal junction. These positive and negative ions are nothing but the depletion region. Since the metal has a sea of free electrons, the width over which these electrons move into the metal is negligibly thin as compared to the width inside the N-type semiconductor. So the built-in potential, or built-in voltage, is primarily present inside the N-type semiconductor. The built-in voltage is the barrier seen by the conduction band electrons of the N-type semiconductor when trying to move into the metal. To overcome this barrier, the free electrons need energy greater than the built-in voltage. In unbiased Schottky diode, only a small number of electrons will flow from N-type semiconductor to metal. Built-in voltage prevents further electron flow from the semiconductor conduction band into the metal. The transfer of free electrons from the N-type semiconductor into metal results in energy band bending near the contact. For forward biasing, the Schottky diode is forward biased when the positive terminal is connected to the metal and the negative terminal is connected to the N-type semiconductor. When the applied voltage is greater than 0.2 volts, the free electrons gain enough energy to overcome the built-in voltage of the depletion region, resulting in electric current flowing through the diode. If the applied voltage is continuously increased, the depletion region becomes very thin and eventually disappears. And for reverse biasing, the Schottky diode is reverse biased when the negative terminal is connected to the metal and the positive terminal is connected to the N-type semiconductor. When a reverse bias voltage is applied, the depletion width increases and the electric current stops flowing. However, A small leakage current flows due to the thermally excited electrons in the metal. If the reverse bias voltage is largely increased, a sudden rise in electric current occurs, which can damage the device permanently. VI characteristics of Schottky diode. The VI voltage current characteristics of Schottky diode is shown in the figure below. The vertical line in the figure represents the current flow in the Schottky diode, and the horizontal line represents the voltage applied across the Schottky diode. The VI characteristics of Schottky diode is almost similar to the p-n junction diode. However, the forward voltage drop of Schottky diode is very low as compared to the p-n junction diode. The forward voltage drop of Schottky diode is 0.2 to 0.3 volts, whereas the forward voltage drop of silicon p-n junction diode is 0.6 to 0.7 volts. If the forward bias voltage is greater than 0.2 or 0.3 volts, electric current starts flowing through the Schottky diode. In Schottky diode, the reverse saturation current occurs at a very low voltage as compared to the silicon diode. Here are some applications of Schottky diode. 1. It is used as rectifiers. 2. It is also used to clamp voltage. 3. It is used in switching device. Here are some differences between Schottky and p-n junction diode.
Thank you, and please subscribe.